Shanghai has a space problem. With 24 million people packed into one of the most densely populated cities on Earth, the only place left to expand is straight up. Enter the Shanghai Tower. It rises 632 meters into the sky, spanning 128 stories. But putting an 850,000-ton structure on this specific plot of land is a logistical nightmare. This diagram illustrates the three forces trying to tear a skyscraper down. You usually want to avoid places where lateral wind forces pummel the sides, tectonic plates shake the bedrock, and the ground itself is made of soft clay. Shanghai has all three. This simulation demonstrates the immediate threat right under the surface. The city sits on a shallow water table that actually collapses under the intense weight of modern development, deflating like a punctured air mattress. To solve these highly modern problems, the engineers constructing this tower had to look backward, borrowing techniques from history's most brilliant minds. With 16,000 people occupying a single 128-story structure, every engineering choice is a matter of survival. Any inability to neutralize the local environment would result in a structural failure of massive proportions. The first obstacle is at the base. You have to figure out how to stop 850,000 tons of steel and glass from sinking into 200 meters of squishy soil. The answer comes from 1889 Chicago. Engineer Dinkmar Adler faced a similar layer of soft peanut butter-like clay that couldn't support the weight of heavy stone walls. This cross-section shows Adler's solution, a reinforced concrete raft. Instead of forcing columns deep into the muck, this flat pad takes concentrated downward pressure and spreads it out evenly across a wide horizontal base. The Shanghai team took Adler's raft and supersized it. They executed a massive, continuous 60-hour pour, laying down 61,000 cubic meters of concrete, a volume rivaling the initial construction phases of the Hoover Dam. This enormous mat distributes the building's load perfectly. It prevents the structure from settling unevenly, ensuring the tower doesn't develop a microscopic tilt at ground level that would become a deadly lean 600 meters in the air. With the base secure, the next hurdle is getting the structure to actually reach 128 stories. Historically, height was restricted because heavy stone walls would eventually crush the lower floors under their own immense mass. The fix originated in 1796 at this unassuming brick structure in England, the Ditherington Flax Mill. Here, engineer Charles Baige moved the load-bearing weight completely off the walls and onto an internal iron frame. The Shanghai Tower relies on this exact principle. It utilizes a massive, lightweight steel lattice to hold up the floors. Because that skeleton bears the load, the outer skin of the building can be made entirely of suspended glass. But a 128-story building is useless if you have to take the stairs. In 1852, Elisha Otis solved this by inventing an emergency brake that slams a falling elevator to a halt, making vertical living safe and practical. By combining Babbage's internal steel skeleton with ultra-fast modern elevators traveling at 18 meters per second, the structure ceases to be an empty monument. It functions as an active, breathing city in the clouds. At extreme altitudes, a new enemy attacks the structure. Hurricane-force winds buy the upper floors with over 90 pounds of pressure per square foot. This diagram illustrates what happens when wind hits a flat, square building. It splits and forms alternating, swirling pockets of low pressure on the sides. This is known as vortex shedding, and it can violently shake a tall structure. To counteract this, designers relied on the work of Jack Cermak. In the 1950s, Cermak pioneered the use of large wind tunnels, specifically tailored to simulate the chaotic, unpredictable turbulence found in urban environments. Testing scale models in these massive tunnels dictated the Shanghai Tower's final form. The engineers realized the building needed a twisting, tapered profile. They also carved a continuous V-notch down the spiral. This precise geometry breaks up the wind currents cleanly, so they can't form violent vortices, reducing the overall wind load by 24%. This iconic corkscrew profile acts as a functional aerodynamic shield, actively breaking apart the wind currents that would otherwise shake the tower to pieces. There is still one force capable of taking the building down. Shanghai sits in a level 3 seismic zone, where a strong earthquake would simply snap a rigid 600-meter structure in half. The defense strategy here mimics ancient Japanese pagodas. These structures survived massive quakes because their layered wooden floors move independently, creating friction that absorbs the seismic shock. Fast forward to the 1970s, when engineer William Lemessurier faced extreme swaying issues in Boston's John Hancock Tower. He solved it by installing a massive internal counterweight. This cross-section demonstrates the modern evolution of those ideas, a tuned mass damper. Located on the 125th floor of the Shanghai Tower, it's a 1,200-ton steel block acting as a pendulum. When an earthquake pushes the building left, the heavy weight swings to the right, canceling out the kinetic momentum. Suspending the weight of 600 cars near the roof sounds counterintuitive, but this crown jewel keeps the tower's center of gravity stable during a disaster, allowing engineers to build the rest of the structure with less rigid steel, making the entire project lighter and cheaper. Today, the fully functional 632-meter marvel dominates the Shanghai skyline. It took 15 years of rigorous planning and 7 years of construction to conquer the sinking soil, the typhoon winds, and the constant threat of earthquakes. In hyper-dense cities like Shanghai, where geographic and environmental constraints limit expansion, these vertical engineering strategies offer a proven template for safe, high-density habitation. The Shanghai Tower stands as a 632-meter testament to the power of adaptation, scaling history's most brilliant engineering breakthroughs to meet the demands of a new millennium.